Now I would like to explain about the applications of Bayes-Savart's law. So first, the definition of magnetostatics. The study of constant magnetic fields or time invariant magnetic fields is called magnetostatics. So constant magnetic fields means the magnetic fields which are constant with respect to time. The constant magnetic fields can be produced by using either permanent magnets or electromagnets. So the study of constant magnetic fields or time invariant magnetic fields is called magnetostatics. So next, the applications of Bayes-Savart's law. So by using this law we can find the magnetic field intensity and magnetic flux density due to different current carrying conductors. So example, straight current carrying conductor or a circular current carrying conductor. So we know that the Bayes-Savart's law formula, the magnetic field intensity H bar equals to I dl bar cross R bar by 4 pi R cube. Units are ampere turns per meters. So next, the magnetic flux density B bar equals to mu into H bar. So this is the formula of magnetic flux density. Here mu is permeability, magnetic permeability, and mu equals to mu naught into mu r. Mu naught is permeability in free space. Its value 4 pi into 10 to the power of minus 7 henries per meters. It is always constant. Next, mu r is relative permeability. Mu r value depends on type of medium. So next, the derivation of magnetic field intensity due to infinite length current carrying conductor. Infinite length current carrying conductor. So consider an infinite length current carrying conductor along the z axis from minus infinity to plus infinity. So assume the current direction is upward direction, means z direction. So next, let a point P at a distance of r from the origin at which the magnetic field intensity is to be measured. So here first we have to find the differential magnetic field intensity at point P. Next, by integrating the differential magnetic field intensity we can find the total magnetic field intensity. So next, by using the relation between B bar and H bar, that is magnetic flux density and magnetic field intensity, we can find the magnetic flux density expression. So consider a differential length of the conductor dl at a distance of z from the origin. So here r bar vector is differential length conductor to point P distance vector. Okay, the current element means, so current into differential length of the conductor is called current element. So current element is I into dl bar. So r bar vector is the distance vector between current element to point P. So we know that the Bayes-Savart's law formula, dH bar equals to I dl bar cross R bar by 4 pi R cube. So first we find r bar vector. So r bar vector is the distance vector between current element to point P. We can find this vector by adding these two vectors. So r bar vector equals to minus z into az bar plus r into ar bar. So r bar vector direction, current element to point P. So first we find current element to origin vector, it equals to minus z into az bar. So next, to origin to point P, vector is r into ar bar. So finally the distance vector r bar equals to minus z into az bar plus r into ar bar, or r bar equals to r into ar bar minus z into az bar. So next, the magnitude equals to modulus of r bar, it equals to square root of r square plus z square. So next, dl bar vector. So dl bar means differential length vector of the conductor. So here current direction, positive z axis direction. So current unit vector is az bar. So next, length of the conductor, differential length of the conductor is dl. Here the conductor located on z axis. So differential length of the conductor means differential length in z axis. So dl bar equals to dz into az bar. If we consider the conductor on y axis, then the differential length of the conductor equals to dy into ay bar. So but here we consider the conductor along the z axis. So differential length of the conductor equals to dz into az bar. Here type of coordinate system we assumed cylindrical coordinate system. That's why unit vectors are AR bar, A pi bar and AZ bar. So now substitute DL bar and R bar vectors in DH bar expression. So DH bar equals to I into DL bar equals to DZ into AZ bar cross R bar vector equals to R into AR bar minus Z into AZ bar divided by 4 pi into modulus of R bar equals to, so root of R square plus Z square, root of R square plus Z square. So modulus of R bar cube equals to R square plus Z square whole power 3 by 2. So next the differential magnetic field intensity DH bar equals to I into DZ by 4 pi into R square plus Z square whole power 3 by 2. So here apply cross product. So AZ bar cross AR bar equals to A pi bar. So R into A pi bar. Next one AZ bar cross AZ bar. AZ bar cross AZ bar equals to 0. So the second term becomes 0. So the differential magnetic field intensity expression DH bar equals to I into R dz into A pi bar by 4 pi into R square plus Z square whole power 3 by 2. So in order to simplify this equation, so let Z equals to R into tan theta. So next by differentiating Z expression dz equals to R into secant square theta into d theta. Here the conductor lies on Z axis from minus infinity to plus infinity. So integration limits minus infinity to plus infinity. So convert the limits into in terms of theta. So at Z equals to infinity, theta equals to, so theta equals to tan inverse of Z by R. At Z equals to infinity, theta equals to tan inverse of infinity. So tan inverse of infinity equals to pi by 2. At Z equals to minus infinity, theta equals to tan inverse of minus infinity. Tan inverse of minus infinity equals to minus pi by 2. So in terms of theta, now the limits becomes minus pi by 2 to plus pi by 2. Lower limit minus pi by 2, upper limit plus pi by 2. So dH bar equals to I into R, dz equals to R into secant square theta into d theta into A pi bar divided by 4 pi into R square plus Z equals to R into tan theta. So Z square equals to R square into tan square theta whole power 3 by 2. So dH bar equals to I into R square secant square theta into d theta into A pi bar by 4 pi into, by taking R square common, R square into 1 plus tan square theta whole power 3 by 2. So dH bar equals to I into R square secant square theta into d theta A pi bar by 4 pi into R square power 3 by 2 equals to R cube. 1 plus tan square theta equals to secant square theta. So secant square theta whole power 3 by 2 equals to secant cube theta. R square by R cube 1 by R secant square theta by secant cube theta 1 by secant theta. So next equation becomes dH bar equals to I by 4 pi R 1 by secant theta. Here 1 by secant theta equals to cos theta into d theta into A pi bar. So next by integrating this expression, H bar equals to integral dH bar, it equals to integral I by 4 pi R into cos theta into d theta into A pi bar. Here limits, lower limit minus pi by 2, upper limit plus pi by 2. So H bar equals to, by taking constant terms outside, I by 4 pi R into A pi bar integral minus pi by 2 to plus pi by 2 cos theta into d theta integral cos theta equals to sin theta, limits minus pi by 2 to plus pi by 2. So H bar equals to I by 4 pi R into A pi bar sin pi by 2 minus sin minus pi by 2, sin pi by 2 equals to 1, sin minus pi by 2 equals to minus 1, minus into minus plus 1. So next equation, H bar equals to I by 4 pi R into A pi bar sin pi by 2 plus 1 minus sin of minus pi by 2. So minus into minus plus plus 1. So 1 plus 1. So it equals to H bar equals to I by 4 pi R into A pi bar into 2. So H bar equals to I by 2 pi R into A pi bar. So this is the expression of magnetic field intensity due to infinite length current carrying conductor. So for a finite length current carrying conductor, the magnetic field intensity expression in previous derivation, in place of minus pi by 2 substitute theta 1, in place of pi by 2 substitute theta 2. Then we get the finite current carrying conductor magnetic field intensity expression. So H bar equals to I by 4 pi R into A pi bar sin theta 1 minus sin theta 2. Units are ampere turns per meters. So So by using these equations we can find the magnetic flux density expression by using the relation B bar equals to mu into H bar. So B bar equals to mu into I by 2 pi r into A pi bar, infinite conductor magnetic flux density expression. Finite conductor magnetic flux density expression B bar equals to mu I by 4 pi r into A pi bar sin theta 1 minus sin theta 2 Tesla. For a finite conductor magnetic field intensity expression.